So last time we did the following examples, and we have seen how to use differential relations to get relations between position, velocity, and acceleration. Let us do some other practice problem. We have a rocket that is traveling upward at 75 meters per second. When it is 40 meters from the ground, the engine fails. Determine the maximum height reached by the rocket and its speed just before it hits the ground. So in this problem, we have a rocket. Initially, the engine was working. So it can be accelerating maybe, or it can be moving at a speed that is controlled by the engine. Now, when the engine fails, this means what? This sentence means what for you, the engine fails?
Acceleration becomes 0.
No, not acceleration equals 0, but the force of the engine on the rocket is not present anymore. Okay? So if you take into consideration your rocket, now when the engine fails, it will only move under the effect of which force?
V0.
Yeah, V0 is not a force under the effect of the weight, okay? But since it has an initial velocity, and because when the engine fails, the velocity was at a certain value. The value here is given to be 75 meters per second. So you know V0, okay? So I know the initial condition for velocity. Now, this problem requires combination of kinetics and kinematics. You know that we need to know A and to get V, to relate it to V. Why we introduced this problem in this chapter and we didn't yet introduce kinetics? Because this is projectile motion. And for projectile motion, without doing Newton law, when a body is only subjected to the effect of the weight, you can directly say that the acceleration is restricted to the gravitational value of G. Because if you remember in the introduction of the course, we took this simple example. So whenever you have projectile motion, the only force is the weight. And then if you write in Newton law, sum of forces equal ma, here you will only have acceleration along y direction. Okay, and if you replace F by W and W is mg, you will get simply that the acceleration is equal to G. Okay, so you can directly use this result whenever the only force acting on your particle is the weight. So now, until now in this problem, we know the initial velocity at which the projectile motion starts. It's 75 meters per second. So this is V0. We know at this stage what is the height of the particle. It's 40 meters. So this is S0. So this is position 0 for us. And we know that the acceleration is restricted to the vertical component AY, which is equal to minus G. Can you please mute your microphones if you are not asking questions? Okay, so
Professor,
yeah,
your voice is lagging a bit. I think the internet connection isn't very stable.
I will try to change my place. Okay.
Okay, thank you.
Yes, 1 minute. Is it better now?
Yes, it sounds better now.
Okay,
thank
fine.
you.
Welcome. Okay, so now what they want us to determine, yeah? Yes, I'm hearing you. Tell me.
Yes. ليش الانجن مش عم يعمل فورس؟
لأنه هن قالوا لي the engine fails. Okay? يعني suddenly
ليش الانجن مش
يعني
عم
for
يعمل
example, if you are in a car
like...
and you stop putting your يعني إذا بتشيل إجرك عن البنزين, the engine will fail. You will not give any more a driving force for your car. So the engine phase, when you don't يعني ما بتقعد تعطي command to the to your system to put a force on it. Okay? أو يمكن ينتزع السيستم. This is another option. It can fail. If you have any failure in the system, it will stop to work, and then you cannot anymore have a force developed on your rocket. So it will only move under the effect of its weight. Okay?
Okay.
Okay. So now we know the initial conditions for velocity and position. We know the acceleration. Let us see what they want us to find. They want us to find first the maximum height reached by the rocket. When I reach the maximum height, what is the characteristic at this level?
V equals 0.
V0.
Exactly. V0, because at this stage, I will change sense of motion. I was moving up, and at a certain stage, because the acceleration is downward, when I move upward, I have a deceleration phase. So my velocity will be reduced in magnitude until reaching a value of 0. When I reach a value of 0, this means that I reached the maximum height of my path. And now my rocket will move downward. Okay, so in the downward motion phase, I have acceleration or deceleration.
Acceleration.
Acceleration.
Exactly, because in the upward motion, so in phase 1, upward motion, V positive, A negative, so they are opposite sign, and we said that when V and A are of opposite sign, I have a deceleration phase, while in phase 2, when I'm moving down, V will become negative and A will stay negative because A is constant here, it's equal to minus G. And then in the downward motion, it's acceleration. Now, I want to find H max in the easiest possible way. What do you suggest to use here? Which formula to get H max in one step?
Can we use V squared minus V0 squared equals
Yes,
to 2AD?
very good. Why? Why we should think about the relation independent of time? Because
Because we
here,
don't have time.
yes, they didn't mention anything about time. It's true that I can find the time needed to reach B and then replace into the position equation, but then I will do it in 2 steps. So it will take more time. Always try to do it straightforward. So the easiest method to apply here is to say, I know for this is point 0, I will call the maximum height position 1. So I have 2 positions to deal with. I know for the initial position, my velocity and my coordinate. For the final position, I know that the velocity should be 0, but I want to search for the coordinate. I want to search for S of B measured from the ground level, which will represent the maximum height I can reach. Okay, so I can deduce then that the easiest way to do is to relate velocity and position through the equation V squared at position 1 minus V squared at position 0 equals to, now acceleration, as we said, is minus G. So it's minus 2G because V squared final minus V squared initial equals 2A delta S. So, and A is minus G, so it's minus 2G S of B minus S0. Okay, so in this way, I found a relation between the final velocity and the final position. Now, if I replace in my equation, what is the only unknown in this equation?
SB.
Exactly, the velocity at point, SB, VB is known, so VB is 0, V1 cancel out. I replace V0 by 75, I replace G by 10. Look, in general, G is 9.81, but for simplification, we can take it 10. So if they don't specify for you, it's fine to use 10. Okay, I don't mind. And the variation in calculation will be very small. Okay, so this is how I can find SB. Now, if I didn't pay attention for this method, what I should do then, I should do two steps. Another way will be to say, what is the time needed to reach point B? How to get this time? Which equation you will use to get the time needed to reach point B?
V equals AT plus V0.
Exactly. So if you use the equation of velocity related to time, you can write that because we are dealing with constant acceleration, you can directly apply all formulas we have seen together. Okay, so in this problem, you have the right to directly use the formulas. You say that VB is equal to acceleration times t plus V0. And I know that V0 is 75. I replace. I know that VB is 0. I know that my acceleration is minus 10. So I can get the time t needed to reach point B. And once I get TB, to get SB, what can I use? What can I use now in a second step?
The third equation, x equals half AT squared plus B0 t plus x0.
Yes, exactly. So now I can use the relation between position and the time. So I can write that S of B is equal to half G t square minus half G, because A is minus G. So it's minus half GTB square plus V0. What is V0? V0 is the velocity at A, which is 75. Okay, so plus 75t plus S0, and S0 is S at point 0 is equal to 40. So by replacing TB in this equation, I will get back exactly the same result, which is that the maximum height is given by SB. Okay, so of course the other method is much simpler, because in the other method I can directly determine from one step the maximum height. Okay, now second question is to find the speed just before hitting the ground. What should I do then now?
Professor, I wanted to ask you a question.
Yeah.
I want to ask هون لأنه أخذنا ال A هي minus G as negative. دايما بس تكون لتحت الاكسلريشن ناخذها minus.
لا حسب الواي axis. Okay, انت in this problem how is your coordinate y, up or down?
Did we take it up?
Yes. Why we take it up? Because look, y of A يعني y0 شو حسبناها plus 40 or a negative value?
Okay, plus 40.
Okay, since we considered y of A plus 40, this means that we considered that the reference is the ground, okay, and y-axis is positive up.
Okay, هلا فهمت.
Okay, you can take y-axis downward, it's not wrong, but if you take y-axis downward, first you should specify your reference. If you keep your reference at the ground and take y-axis positive down, then you take y of A minus 40, and the acceleration then will be plus 10.
Okay. هلا فهمت.
So
Thank
you
you,
are
Professor.
you are free to select the coordinates that you want, but you should respect it. You should respect it in the sign of your velocities and in the sign of your positions.
Okay, Professor, thank you.
Welcome. Any other question? Okay. Now, the second part in this problem is to determine the speed just before hitting the ground. How you will determine the speed just before hitting the ground now? What should we do?
The first thing that we know إنه x بتكون equals to 0. Oh,
Exactly. We know y final. Y final is 0. Okay. Which relation you can use here?
Between yes, the one that we use this in the second method.
Exactly. Look, here it's exactly the same equations we used before. So you can use, if you want, the v square final minus v square initial equal to 2a delta s, or you can use the second option to find the time and then replace in s. And the two states where you want to apply this relation, v square final minus v square initial equal to 2a delta s, you have several possibility of choices. Why? Because here it's true that you have two phases up and down, but both are characterized by same acceleration, which is minus g. Okay, so you can directly apply this relation from state 0 to state 2. Or another possibility is to say, because I found the properties at point 1, I can also apply this relation between point 1 and 2. Both will give you exactly the same result because the two phases are sharing the same acceleration. So they are driven by the same equation, even if one phase is acceleration and another is deceleration, but equations are the same. Now, which one you should select? Which one is safer to use, point 0 or point 1? Which one is safer to use? Look, 0, I have it completely from the given. At point 0, they gave me the initial velocity and they gave me the initial position. Okay. While على point 1 أنا عملت calculation ل SB. So if I did a calculation error in SB, then this will affect my results. I will get a wrong answer for point 2. This is why I always advise you, if possible, select the points that are completely given. If not possible, then you can rely on your calculations. And of course, I will follow you. If you did an error in calculation of SB, I will follow you in the second step. But it's you will take like maybe 85% or 90% of the grade. But to not lose the remaining part and to be on the safer side, try to use given. If you can rely only on given, it's better. So this is why I will do the relation between point 0 and point 2. So now if I apply, yes.
Can I ask you a question?
Yes, sure.
However, here نحن أخذنا على point 0 تبع ال SA is 40 meter. But here we have VA لما تكون الروكت going upwards. نحن لما ترجع توقع إنه مش هتكون غير شيء السبيد.
بس ما أنا أصلاً أنا عم باخد الستيت 1 هي وطالعة، مش هي ونازلة، وما حتكون غير السبيد. You know why؟ وقت ترجع توصل لهون حتكون velocity downward بس حتكون 75 meters per second. You know why?
Why?
Because you have conservation of mechanical energy here. You don't have any source of loss. You don't have friction. You are neglecting air resistance.
Okay.
Okay, so here there is no loss of energy. So when you go back to the same state, you will reach it with the same total energy. And since you are at the same position, this means your potential gravitational energy is the same. So also your kinetic energy should be the same. So in magnitude, the velocity will be the same, but instead of being up, it will be down.
I understand هلا. Okay, deal. So لأنه من وراء conservation of mechanical energy فينا نعمل هيك.
What?
So من وراء conservation of mechanical energy فينا نعمل.
Exactly. من وراء conservation of mechanical energy. Yeah.
Okay, thank you.
Welcome.
بس دكتور إذا 75 ضلت constant مش معناتها الأكسلريشن راحت للزيرو؟
لا انتبه على شغله، ما هي الفكره انه انت الاي look هيدي بس instantaneously 75 هي وطالعه ما بتضل 75. As you are moving up, the velocity will decrease from 75 to what? It will decrease until reaching zero here. Now when you move down, okay, when you move down عندك like asymmetry in positions. يعني when you pass by the same positions, you will have exactly same magnitude of velocity, but it will be of opposite sign. يعني it will be negative instead of being positive. يعني بس ارجع امرق بنفس level, I will be at the same magnitude of velocity, but I have opposite sense.
Okay.
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 And you can test this. Look, you can test this with your equations. You know that using your equations, S of when you put, for example, velocity. Okay, so you have the velocity, or for for a certain position, SB. The equation is minus 5t squared. Okay, plus 75t. Okay, and the plus v0, which is plus s0, which is 40. If you solve here for what times you will reach a certain position, okay, you will see that you have two times, one corresponding to the upward motion. So you have a certain, when you solve this equation, this is a second degree equation. So if you fix SB, for example, let's say at 45, I need to know at which times my rocket will pass by SB equal 45 meters. If you solve this second degree equation, you will get two solutions. The first one will correspond to your upper motion. The second one will correspond to your downward motion. And when you replace these two times in the equation of V, you will obtain exactly same velocity magnitude, but opposite sense. So one is positive, one is negative. And we'll do so together one problem of analysis where you will demonstrate mathematically this. You will demonstrate that they will have same magnitude, but opposite sense. Okay. Any other question on this?
Can I ask a question?
Yes, sure. But let me check your chats. Okay. Yes, tell me.
Can you just repeat what's this, how we find the speed just before it hits the ground?
Yes, sure. We didn't finish it yet. I will do it now. Okay.
Oh, okay. Thank you.
Okay. So we said that because the whole motion is characterized by the same acceleration, which is ay equals to minus g. Okay. So I can apply the rule of v square final minus v square initial equals 2a delta s between any two positions of my path. So I can apply it between this point and the initial point and the final point of interest, or also I can apply it between B and the point of interest. Both will give me the same result. But to not rely on my calculation at B, it's better to select this point. So I will apply it between 0.0 and 0.2. If I write this relation, I can write that V2 squared, which is the velocity of the rocket just before hitting the ground, minus V at point 0 square is equal to 2a delta s, and a is minus g, so minus 2g, and g is 10, so minus 20 delta s. Now what is delta s? Delta s is s2 minus s0. Okay, now since I reached the ground, then I know that s2 is 0. Okay, because my origin of y-axis is at the ground level. So I can simplify S2, and I know that S0 is 40, so I replace by 40. And I know that V0 is the initial velocity when I was at point 0, it's 75, I replace. The only unknown in this equation is V2, which is the velocity just before hitting the ground, so I can calculate. Okay. And tell me, you will select the positive value or negative value for V2, because this equation will give you V2 squared. So it's for you to
Negative.
select the sign. You will select which sign?
Negative.
Negative, because I'm moving down. So at this point, I reach the ground with a downward velocity, which so it's V is so the y component of V is negative. Okay. Any question on this? Okay. So let us move to another problem. We have a metallic particle that is traveling downwards through a fluid that extends from plate A to plate B under the influence of a magnetic field. If the particle is released from rest at point C, which is characterized by S equal to 100 millimeter, and an acceleration A function of position equals to 4s, where s is in meters, determine velocity when the particle will reach plate B and the time needed to travel from C to B. So let us decompose our given to see what should we do. First, in this problem, we have a particle that is influenced by a magnetic field. But the effect of the magnetic field is given because they gave us the acceleration function of position. So here we don't have to do any kinetic analysis because the expression of A is given for us. So we have A function of position. And we know that the initial position of the particle is given. So initially it was at point C. S of C is 100 millimeter. So they gave us the coordinate system also. The coordinate system is a downward axis, downward vertical axis. We know that S of C is 100 millimeter. As I told you before, pay attention for units, okay? Since A is provided in meter per second square, so you should convert all values of S to meter. So this value here, you can say that S of C is 0.1 meter. Okay. And then I know that initially my particle is released from rest. So this means that I have that VC is, so the initial conditions are VC 0 and S of C equals to 0.1. Okay. Now, they want me first to determine the velocity of this particle when it will reach the bottom plate. So this particle is traveling from C downward towards B. So I want to get what will be the velocity of the particle at point B, knowing that S of B is 0.2 meters because they gave me that this distance is 200 millimeters. This means that S of B, here S of B is positive because the axis is positive downward. Okay, I always respect the axis direction I considered at the beginning. So you take a reference and you follow it. Here it's given for me, I should respect it. So SB is 0.2. Okay. And now, what do you think should I use to solve for velocity at B? Which relation?
Can we use, Doctor, the A equal BdV over dx?
Yes, very good. I will use the differential relation involving acceleration, position, and velocity. I cannot use, like in the previous problem, formulas of A constant, because A is function of position. So I say I need to use a relation involving acceleration, position, and velocity. If I go back to my differential equations we introduced last time, we should use AdS equals to VdV. Okay. Now, the next step is to replace A by its formula. So A is equal to 4S. So I just put 4S ds is equal to VdV. And the next step will be to integrate both sides. So as we said, after doing separation of variables, we integrate for both sides. So for this side here, okay, I should integrate between the initial position, which is C, to the final position at B. Look, again, as we said last time, in general, we might need the general equation for next step, because here they didn't only ask for the velocity, they asked also to find the time needed to reach B. Okay, if you do some analysis, if you want to involve the time needed to reach B, which differential equation you will use? You know the initial position, you know the final position. You will get now V, and you want after to relate with time. So
V
what?
equal to dx by dt.
Yes, very good. The next step will be to write V equal ds by dt. So I need the expression of V. I need to know what is V function of position. Okay, this is why I will not do it 2 times. I will directly here pay attention for this and say, let me derive first the general equation between velocity and position, and then replace S at B. Okay, so when I integrate here, I will integrate from the initial condition, which correspond to point C. So S of C is 0.1, and it corresponds to an initial velocity of 0. But for the other boundary, I will make it general. So I will integrate from position C to any other position. So integral from 0.1 to any S. And here I will integrate from 0 to any V. V corresponding, of course, to this position. This will allow me to get a relation, a general relation between velocity and S. And once I find this relation, I can replace SB by 0.2 to get velocity at B. So let me clear and write again. So we will integrate between 0.1 and S for SDS. And from the other side, I will integrate from 0, which correspond to the initial velocity at C, to V of VdV. Now, this is a simple function to integrate. The integral of 4S is 2S squared. So I have 2s square minus, so if I apply at the bound between the boundaries and 0.1, I get 2s square minus 2 times 0.1 square equals to, from the other side, the integral of v with respect to v is v square over 2. So this corresponds to v square over 2 minus 0. So it's v square over 2. In this way, you got a relation between velocity and position. So if you want to get the expression of v, all you have to do is to multiply by 2 this expression. So you get 4s square minus 4 times 0.1 square. And to eliminate the square here, you will do radical of this expression. Okay, this will give you the expression of v function of s. And now, to know the velocity when you reach point B, you just have to do a numerical replacement. You replace s here by s of b equals to 0.2. This will give you the value of VB. Okay. Any question on this step?
Professor, may you repeat what you said at the end, please?
Yes, sure. Yeah. Let me, we will look at it here. Look. So you do separation of variables, you do integration. Okay. You will get the following. You will get, as we said, 2s squared minus 2 times 0.01. Okay. Is equal to v squared over 2. So now to get the expression of v function of s, you multiply by 2 both sides. Okay, so you get the following. You get that v squared is equal to, you can take, when you take 2 to this side, you will get 4 times, I will take into factor s squared minus 0.01. Okay, and now to get v, all you have to do to eliminate the square, you have to do radical for both sides. So if you do radical for both sides, it's equivalent to multiplying by power what? By power 0.5. So all of this will be multiplied by half, exponent half. Okay, and then you get the expression of v function of s. This will give you the general function v function of s. Now, since you are interested in particular in the velocity when you reach point B, you have to get v at B, you have to replace s by s at point B, which is 0.2 meters. So by replacing s by 0.2, you can get what is the velocity of the particle when it will reach the bottom plate. Okay.
Okay, thank you, Professor.
Welcome. Now, next step is to find the time needed to reach B. If I want to find the time needed to reach B, as we discussed together, we need, already we have V function of S. So now we know what is V function of position. And we want to involve time. So we need to use the